Chapter 8, Section 4 is going to take us into rectangles. So what we're going to do is we're going to work from just broad quadrilaterals and start working our way more and more specifically. So we started with parallelograms, and we got some neat ideas out of those. Now we're going to take it a step further and go into rectangles. So as we continue further into this chapter, we're going to get more and more specific with what kind of figures we're talking about. We're going to see that the different properties that they have become more and more specific as we go. So make sure you're keeping up a good list, good notes, so that way you can determine between one figure and another. And again, definitions are everything with what we do here, so keep up with them. A rectangle, here's how we'll define it. A rectangle is a quadrilateral, so that's the first idea, 4 sides, and they have 4 right angles. That's it. That's all we know. 4 sides, 4 right angles, nothing more, nothing less. All right? From these 2 ideas, we can then start getting other ideas. For example, opposite angles would obviously be congruent, right? If I drew just any old 4-sided figure with 4 right angles, well, then it's obvious that opposite angles are congruent. So that means rectangles aren't just rectangles, they're also parallelograms as well. Since they're parallelograms, then that means everything we've learned about parallelograms will apply. However, be forewarned, not everything we learned about rectangles goes in the other direction. All right. All rectangles are parallelograms, but not all parallelograms are rectangles. So we've got to keep that in mind. So what we learned today about rectangles, everything that we've learned about parallelograms will work, but not always in the reverse. All right. So take a look. Let's talk about those specific rectangle ideas, and then we'll go back and kind of look at those parallelogram ideas as well. So some specific rectangle theorems. Take a look. If a parallelogram is a rectangle, so again, those 4 sides and 4 right angles, then that also means the diagonals will be congruent to each other. So in other words, in this case, if I know I've got a rectangle, so 4 right angles, and we've got those 4 sides, then cool. AC and BD have to be congruent. Well, let's see if we can work out as to why that is. So one thing that I'm going to do is I notice that I've got a triangle here. All right. I also notice that I've got a different triangle. Let's see if my red will keep up with my blue. A different triangle. Yeah, that'll work out nice. There. Now, one thing I noticed is that since it's a rectangle, that means it's a parallelogram, so my proof would go something along those lines, Opposite sides would, of course, then be congruent. So that means that AD and BC are congruent. Cool, because it's a parallelogram. I notice also that they have DC in common. All right, wonderful. I notice that angle C is a right angle by what it means to be a rectangle. I also know that D would have the same effect. So I have a right angle here and a right angle here. Well, by side, angle, side, these 2 triangles are congruent. If the triangles are congruent, then that means these diagonals are congruent by CPCTC. So not only do they bisect each other because we're dealing with a parallelogram, these diagonals now are also congruent. So that would be my informal proof of it. Obviously, you could write all that out and make a formal proof from it, but that's my informal proof of how I know that AC and BD have to be the same. All right? Now, take a look. If the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. This is a converse. In other words, this is a test to see if what we have is a rectangle. All right? So one way we could prove it is if we have those 4 right angles. Another way to prove it is if we have a quadrilateral and our diagonals are equal to each other. If they are, then happy days, we've got enough to prove that indeed we've got a rectangle. Now, the question, of course, is how do you go about doing that? And I'll let you work that out. But notice the way the proof is written, if a parallelogram, all right? So if we know it's a parallelogram, then just kind of help you out. So if the diagonals of a parallelogram, well, we already know that AC and BD are the same. Cool. Doesn't that mean that AD and BC are the same? And doesn't that mean that DC and CD are the same? Well, wonderful. We can do that. Once we know that those three sides are the same, we could use a little bit of right triangle work to say, oh, look, they're the same. Right? And I'll let you do that on your own. But that one is a very good proof to try and work through. And again, fairly simple and straightforward. All right, some other important ideas. All right. Now, a lot of these you're going to notice borrow from what we did with parallelograms. So we've got ourselves just sort of a nondescript rectangle here that we can work through. So opposite sides are congruent and parallel. So again, that we get that based on our parallelogram work. So I'm going to draw us a little parallelogram in here just to remind us that's where we pull that from. So AB and DC are the same. AD and BC are the same. Of course, those opposite sides are also parallel. Opposite angles are congruent. And again, we also pull that from our work in parallelogram. So A and C are the same, B and D are the same. Consecutive angles are supplementary. Again, we also know that from our work in parallelograms. Cool. And again, we could add A and B together and get 180 and so on. Diagonals are congruent. All right, well, that is specifically a rectangle issue. And bisect each other. Well, we said that that was a parallelogram issue. All right? And that all angles are right. All right, well, that is a specific rectangle issue. Now, notice what I've done here, folks. I've gone through and figured out what is specific to being a parallelogram versus what is specific to being a rectangle. So again, everything that's marked with a parallelogram will also apply to the rectangle. But these ideas that I've marked as a rectangle don't apply to every parallelogram. So again, be aware. We're going to get even more convoluted as we get into some other figures. But again, start making those lists now so that you know what goes where. Right? And again, you've got a good start here with the notes. Let's take a look at some example questions that you can see with all of this and see what we can do. So again, we've got a quadrilateral, so there it is, and we know that it is a rectangle. So one thing I'm going to do real quick is go ahead and mark in these right angles, just to remind myself that it's not just any old parallelogram, it is specifically a quadrilateral that has right angles, so rectangle. All right, if NQ, so this little segment here is 5x minus 3, and QM is 4x added to 6, find NK. Now, first off, how do I know that this and this are going to end up being the same? Because that's how they're setting us up. Well, remember, we know that the diagonals will bisect each other, and we know that the diagonals will be congruent. So cool. If this whole distance and this whole distance are the same, and we cut them in half, then their halves will also be the same. Cool. So let's work through this here real quick. So we've got 5x subtract 3 is going to be equal to 4x add 6. Subtract 4x on each side, that's x. Add 3 on each side, that's 9. We need to find NK, so this entire distance. So I'm going to do 2 times 5x minus 3. And again, that 5x minus 3 was just one portion of it. Let's see, that would give me 10x subtract 6. We'll put our 9 in there. So that is 90 subtract 6, or 84. Cool. So 84 units, whatever that may be. So you get the idea. Working through these is just a matter of labeling things and going from there. One thing I do notice, though, for number 12, and I do want to work with you all, is this idea of the quadratic. So let's see if we can do that one as well, because these others are going to follow similar lines. No pun intended. I think you'll be good to go with that. Let's try this one. NM is 8x subtract 14, so I'll label that. JK on the other side is x squared add 1. All right, and we're trying to find JK, that distance. So we could say that x squared add 1 is equal to 8x subtract 14. So one thing I'm going to do is try and get everything over here on the left-hand side. So x squared subtract 8x add 15 is equal to 0. All right, I'm going to try and factor this out, just because I don't want to use the quadratic formula if I don't have to. Factoring is a lot faster. Let's see, x and x would give me x squared. I need factors of 15 that when I multiply them, obviously, we'll get the 15, and if we add them, we'll get a negative 8. Well, I think 3 and 5 would do that just nicely. 3 times 5 negative, that is a positive 15, and then adding those would give me my negative 8. Looks good. So x could be 3 or 5, depending on our situation here. So if we plug that in for x squared add 1, we could have two different answers. One version is 3 squared plus 1. We could also do 5 squared, add 1, and obviously both of those answers could be right, or only one of them, depending on the parameters that we might have. In this case, they don't give us any other parameters, so we'll work on both. 9 added to 1 is, of course, 10. 25 added to 1 is, of course, 26. And again, either of those would be acceptable answers. But again, just some work with quadratics. It's been a while since we've done it. Let's try our work with angles. All right, so in this case, I know that angle 1 is 30 degrees, so that one's easy. Let's see if we can find the others. Well, notice angle 4 is another one that we need, and since these two are going to be the same, 4 is also 30. Angle 7, well, I notice that 7 and 2 are going to end up being the same. And of course, we have a right angle here, so that means angle 2 is 60, which means angle 7, yep, also 60. Angle 3, I've lost angle 3. There it is. We'll have an isosceles triangle here. These are the base angles, so 60 there as well. Where's angle 8? I've lost angle 8. There it is. Again, we've got an isosceles triangle, so 30 and 30. And that leaves angle 9, so that's this angle here. Well, notice if we have 60 here for angle 2 and a 60 here for angle 3, well, then that means 10 is also going to be 60 to get us back to 180. 10 and 9 are vertical, so another 60-degree angle there as well. So these are the kinds of things that you'll see. Again, you've got to know the difference between our parallelograms and our rectangles to know what are those key characteristics they're going to help us figure out what we need to do in different problems. Right? Again, if you have any questions or concerns, bring them with you to class. Otherwise, have a good day, folks.